Optimus Gen 3 has been redesigned by Tesla to become a homeworker robot that's easy to manufacture and affordable. With a 22-pound weight reduction, a simplified structure, and fewer components, the robot is now optimized for large-scale casting using the 50,000-ton Giga Press. This massive machine, now operating in Texas, produces major body parts like the chest, back, and legs more quickly, precisely, and cost-effectively. How did the Giga Press become the key to mass-producing humanoid robots? Before we begin, please help us reach 9,500 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Bot, Tesla EVs, and the latest news. How does the 50,000-ton Giga Press influence the design of Optimus Gen 3? Tesla didn't redesign Optimus Gen 3 to make it prettier. It was redesigned to be mass-produced using ultra-large casting technology, specifically the 50,000-ton Giga Press. This is one of the most powerful alloy die casting machines in the world, developed by Tesla with a singular goal: to take humanoid robots out of the lab and into large-scale industrial production at minimal cost. Earlier versions like Generation 1 and Generation 2 were still bulky, structurally complex, and mostly hand-assembled. Generation 3 marks a leap forward. Its weight has been reduced by 22 pounds, its modularity improved, its joints made more flexible, and most notably, components like the chest, back, and leg frames have been completely redesigned to support one-piece casting with the 000T Giga Press. This is not just a technological upgrade, it's a fundamental redesign of the robot from the ground up. The philosophy of design for manufacturing has been fully embraced. Every component must be shaped to allow for single-shot casting, no multi-part assemblies, no complex welding, no manual screwing. The Gen 3 Optimus frame now resembles a monolithic skeleton, hollow inside to house motors, batteries, and the central computer, yet still lightweight, strong, and precise enough for long-term operation. The Giga Press enables casting of metal parts with ultra-low tolerances less than 0.1 millimeters, ensuring near-perfect alignment between components, something traditional assembly methods struggle to achieve at high volume. The arrival of the 50,000-ton Giga Press forced the Optimus design team to abandon the old architecture with hundreds of discrete parts. Instead, the entire design had to conform to casting principles: simplified cross-sections, stable alloy flow, no dead corners, easy mold release, and the integration of multiple functions into a single cast piece. For example, the chest of Optimus Gen 3, which houses the battery, central computer, and major sensors, is no longer a complex assembly of shells, brackets, and frames. It's now a solid, seamless alloy block cast by the Giga Press. This single piece serves as protection, structural support, and a mounting base for all core systems, cutting the number of components by at least 30% and reducing assembly time by more than 50% compared to Gen 2. Thanks to the 000T Giga Press, Optimus is not just lighter, but also stronger. The 22-pound weight reduction lowers energy consumption, extending operating time to 6 to 8 hours per charge. At the same time, the increased structural rigidity from cast components allows the robot to move more stably and safely while performing complex tasks like lifting objects, climbing stairs, or bending to pick things up. But more importantly, these one-piece cast parts are ideal suited for robotic assembly, meaning robotic arms in the factory can install them autonomously without human labor. This marks the first step toward Elon Musk's larger goal: building a factory where robots build other robots, without requiring thousands of human workers like traditional assembly lines. The significance of the 000T Giga Press goes beyond reducing weight and parts. It's the key enabler that allows Tesla to bring the cost of each robot below $20,000. That's a revolutionary figure compared to today's humanoid robots like Boston Dynamics Atlas, estimated over $150,000, or Agility Robotics Digit over $70,000. With the ability to cast hundreds of large parts per day, the Giga Press allows Tesla to drive per-unit costs to a minimum. If the robot's body can be built from just 2 to 3 cast blocks instead of hundreds of smaller pieces, then labor costs, error rates, and inspection time all drop exponentially. In fact, designing for the Giga Press also simplifies maintenance. If part of Optimus's leg frame is damaged, Tesla can simply replace the entire cast piece within minutes, rather than disassembling every joint and metal bar. This simplicity in design translates to simplicity in repair, a critical factor for deploying robots at scale, from factories to homes. Once again, please help us reach 9,500 subscribers. This is important for us to stay motivated. Thank you. What role does Giga Press play in making Tesla bot affordable? The new design of Optimus Gen 3 is not just a technical improvement, but a core strategy for cost reduction. With the goal of bringing the robot's price below $20,000, Tesla had to do something no tech company has ever done: transform a complex humanoid robot into a low-cost industrial product, just as it once did with electric vehicles. And at the center of that cost-cutting strategy is the 50,000-ton Giga Press, a massive alloy casting machine that not only redefines how robots are made, but also drives production costs down to unprecedented levels. While the production cost of a typical humanoid robot like Boston Dynamics, Atlas, or Agility Robotics Digit ranges from $70,000 to over $150,000 due to complex structures and manual assembly, Optimus Gen 3 is designed to be faster, simpler, and drastically cheaper, thanks to its full adoption of one-piece cast manufacturing. Previously, Optimus had a structure made up of hundreds of small mechanical components: screws, subframes, connectors, brackets, sensor housings, many made of steel or high-end materials that are difficult to manufacture. Each part required multiple stages: cutting, welding, polishing, assembly, testing, and adjustment, all of which increased costs, lengthened production time, and made it difficult to assure consistency across robots. But with Gen 3, Tesla shifted toward a design philosophy focused on material minimization, part reduction, and functional integration, all to fully leverage the Giga Press 50T's alloy casting capability. When major sections of the robot, like the chest or legs, are cast as a single solid block, all the costs associated with internal assembly disappear instantly. No need for mechanical engineers to screw together every joint. No need for alignment checks on every connection. No need to fabricate and manage hundreds of individual parts. This is how Tesla slashes thousands of dollars off each robot simply by changing the way the frame is built. Moreover, labor cost, one of the most expensive factors in robot manufacturing, has been drastically reduced through automation. In traditional robot assembly lines, engineers are responsible for delicate tasks like installing arms, mounting motors, wiring electronics, calibrating sensors, and more. But Optimus Gen 3 is designed to be assembled by robots. Robotic arms can automatically pick, place, fasten, and inspect components, no human hands required. As Elon Musk once stated, Optimus will be assembled by other Optimus robots in the factory. That's how we scale. The Giga Press sits at the beginning of that chain, casting parts that are then moved and assembled entirely by machines. This closed-loop production model cuts millions in operating costs every year. Cost savings aren't limited to production. The new design also reduces logistics and inventory costs. With fewer parts, Tesla needs to ship and store fewer components, lowering risks of delays, damage, and simplifying the supply chain. While rival robots may require sourcing hundreds of components from dozens of suppliers across multiple countries, Optimus needs only a few cast blocks and core electronic modules, all of which can be produced in-house at a single gigafactory. This provides long-term cost advantages, insulating Tesla from inflation, raw material price swings, and third-party delays. Optimus Gen 3 is also engineered for ultra-low maintenance costs. Thanks to its modular cast-molded body, Tesla can replace entire damaged sections within minutes, rather than disassembling every tiny component. The low cost of replacement, fast repair time, and reduced error rate make the monthly operating cost of Optimus, whether in a factory or a household, significantly lower than any other humanoid robot. It's this combination of low upfront price and minimal maintenance that makes widespread deployment of humanoid robots truly feasible. Lastly, economies of scale play a decisive role. Tesla can sell robots near production cost because it expects to manufacture hundreds of thousands per year. This mirrors the Model 3 strategy, As volume increases, average unit costs drop dramatically. The Giga Press 50T helps Tesla achieve this with unmatched speed and precision. If each cast takes just a few minutes, then a single line can produce thousands of blocks per day, enough to supply tens of thousands of robots per month. How many Optimus units can Tesla build per month with the help of a 50,000-ton Giga Press? When Elon Musk announced the goal of producing 10,000 Optimus bots per month, equivalent to 120,000 robots per year, the tech world immediately realized that Tesla wasn't merely building a product, but laying the foundation for an entirely new economy, one powered by non-human labor. And the key to realizing that ambition doesn't lie solely in AI software, but in large-scale physical manufacturing, where the 50,000-ton Giga Press and Optimus's simplified casting-based design form a strategic duo. If in the early years Tesla struggled with bottlenecks in assembling the Model 3, then with Optimus, the company is taking the opposite approach, building massive production capacity first, and then popularizing the robot. With the Giga Press, Tesla can cast the main structural blocks of Optimus in just minutes, meaning a single production line can create hundreds of robot parts per day. Combined with a fully automated assembly system, already deployed in Tesla's factories for years, the Optimus production process could reach near-complete automation. More importantly, this process can be replicated globally, just like how Tesla expanded Giga Shanghai, Giga Berlin, and now Giga Mexico. A line built in Texas can be copied to China, India, or Europe, because the entire supply chain, casting machines, robotic arms, and robot design are already standardized. When a company can produce 10,000 humanoid robots per month, over 300 per day, it's no longer just technological R&D, it becomes a human labor replacement industry. With a target cost below $20,000 per unit, Tesla could deploy Optimus across its factories, logistics chains, and even into homes or service companies. A robotic worker can operate 16 hours a day, 7 days a week, without breaks, wages, or strikes. And when Optimus is produced in the hundreds of thousands each year, robot adoption will move from experimental to dominant. Unlike other robotics companies that produce only a few hundred units per year for demonstration or specialized enterprise use, Tesla approaches the market like it did with the Model 3. Build robots the way cars are built, at the highest volume possible. And more importantly, at sufficient scale, Tesla not only reduces cost, but can also use robots to build other robots. Optimus Gen 3's modular design and simplified assembly allow its limbs, joints, circuits, and cast frames to be installed by other robotic arms. Elon Musk once said, "Optimus will be built by other Optimus robots." That wasn't hyperbole. It's a clear strategy, a closed-loop production system where robots build the next generation of robots, enabling infinite replication. When manufacturing no longer depends on human labor, scaling becomes unlimited. The strategic implications of this are profound. First, it allows Tesla to expand its robotic workforce into multiple industries: manufacturing, warehousing, healthcare, hospitality, and more, at a speed no other company can match. Second, it shifts the global labor structure. Repetitive, dangerous, or tedious tasks can be entirely handed over to Optimus, while humans focus on creativity. Tesla and other companies have started to look at manufacturing in a completely different way, said Pedro Pacheco, vice president of research at Gartner. Indeed, a giant press is now reshaping how humanoid robots like Optimus are built. Instead of assembling more than 60 parts, Tesla can cast the robot frame in a single shot, cutting production time and costs by up to 40%. As this Giga casting technology shifts from EVs to robots, how is Gen 3 bot advancing mass production to the next level? Before we begin, please help us reach 8,000 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Model Q, Tesla EVs, and the latest news. What would happen if Tesla applied the 50,000-ton Giga Press to Optimus production? Casting the torso of the Tesla bot using a 50,000-ton Giga Press would fundamentally transform both its structural and mechanical design. Unlike traditional humanoid robots such as Figure 01 or Digit, which rely on modular frames made from hundreds of aluminum and polymer components, Tesla's approach would enable a seamless one-piece structure. Agility Robotics, for instance, revealed that Digit's body consists of over 200 individual parts assembled with screws, brackets, and welds. This not only adds weight, but also introduces potential misalignments and slows down production. In contrast, Tesla's Giga casting method would eliminate separate joints entirely, resulting in a lighter, more durable frame with fewer points of failure. However, to fully capitalize on the advantages of a single casting, the design of Optimus would need to be reimagined from the ground up. This shift would mark a significant departure from conventional robot assembly methods, potentially setting a new standard in humanoid robot manufacturing. Tesla's die-casting approach aims to reduce that number to under 10 structural parts, similar to the Model Y's rear underbody, which was reduced from 70 parts to just 1. With the Tesla Bot, the central chassis could be cast as a single integrated exoskeleton, incorporating mounting points for actuators, battery packs, wire harness channels, and cooling systems all baked into the geometry of the mold. This not only saves assembly labor, but also ensures millimeter or even sub-millimeter tolerances at scale, crucial for joint alignment and smooth bipedal movement. The lighter and denser design also helps keep the total robot weight below 56 kilograms. That's around 20% lighter than competitors like Figure 01, despite Tesla Bot having more joints and higher payload expectations. The reduced part count also improves structural stiffness, which is vital for high-precision manipulation, with Tesla Bot's 11-fingered hand and 2 degrees of freedom wrists. Fewer joints between parts mean less flexing under load and higher energy efficiency, helping the robot run for 8+ hours on a single charge. Finally, with the body cast as one unified part, design iterations become software-driven. Any updates in motor placement or thermal pathways can be reprogrammed into the mold design. This gives Tesla a massive advantage in testing, refining, and evolving the robot rapidly, far ahead of competitors still reliant on traditional assembly methods. Regarding the production process, traditional Giga Press machines with a pressing force of 6,000 to 12,000 tons have been sufficient to cast the rear frame of vehicles like the Model Y or Cybertruck. However, a robot demands much higher mechanical precision due to its smaller, thinner structure and the many cavities needed to house sensors, wiring, motors, and transmission systems. If Tesla applies the 50,000-ton casting mold, it could be an effort to achieve the refinement necessary to integrate many components into a single block of material, such as mechanical joints at the hips or shoulders of Optimus. With a pressing force 4 times greater than the standard Giga Press used in cars, Tesla could produce seamless robot parts while maintaining the required lightweight and durability. In terms of production time, a single 50,000-ton Giga Press can complete what a robot frame in just 30 seconds. Running continuously, one machine could produce around 900 to 1,500 frames per day. With 3 machines working in parallel, Tesla could achieve an annual output of 1 to 1.3 million robot units. Meanwhile, competitors like Figure AI or Agility Robotics still operate on a small scale, taking several hours to assemble a single robot. This creates a massive gap in scalability. The greatest benefit lies in cost reduction. Casting a single piece drastically reduces the number of mechanical parts from hundreds down to fewer than 20 main components. Each assembly step requires labor, time, and quality control. Cutting down assembly stages also lowers error rates, maintenance costs, and simplifies mass production. A robot with a cast single-piece frame could cost only a few $100s for the frame alone, compared to thousands of dollars with traditional methods. Combined with the 4,680 battery cells and electric motors reused from Tesla's electric vehicles, the total production cost of Optimus could be reduced below $20,000. Materials are also a crucial factor. Tesla could use specially formulated aluminum-magnesium alloys, similar to those in aerospace, to achieve an optimal strength-to-weight ratio. A lighter robot, is not only easier to move, but also consumes less energy. This extends battery life, is a critical factor when deploying robots at scale in industrial, logistics, or healthcare environments. The impact on competitors cannot be overlooked. If Tesla can produce millions of Optimus robots annually at a cost 50 to 70% lower than current companies, many robotics startups may need to fundamentally rethink their business models. Firms like Boston Dynamics, known for Atlas and Spot robots, have invested heavily in software and mobility, but have yet to solve the cost challenge. Meanwhile, Tesla applies the automotive philosophy. Mass production is the hardest engineering problem, even harder than AI. The long-term potential is enormous. With the ability to cast millions of precise, lightweight, durable, and affordable robot frames, Tesla could bring Optimus to the mass market, from personal assistants and logistics workers to healthcare aides. Each of these fields represents hundreds of billions of dollars in market opportunity. If the product proves durable, affordable, and intelligent enough, Tesla will not only lead in electric vehicles but also pioneer the global consumer robotics industry. As Elon Musk once said, the robot market could be bigger than the car market. In summary, if Tesla deploys the 50,000-ton Giga Press for the Optimus robot, it would not merely be a technical innovation. It would lay the foundation for a new industrial revolution where robots are produced as quickly as cars, as cheaply as smartphones, and as intelligently as humans learn. If this becomes a reality, the Giga Press would be more than just a massive metal machine. It would symbolize the dawn of the 21st century mass robot production era. Tesla's use of the 50,000-ton Giga Press to cast the body of the Tesla bot marks a significant advancement in the humanoid robot manufacturing industry, highlighting a notable difference from traditional casting machines like the 12,000-ton Giga Press currently used for the Cybertruck. Although both are massive high-pressure casting technologies, these two machines differ completely in terms of objectives, materials, processes, and precision requirements, reflecting two very distinct design philosophies between automobiles and humanoid robots. First, the biggest difference lies in the intended product. The 12,000-ton Giga Press is designed to cast large, high-strength parts, such as the floor frame or rear frame of the Cybertruck components, requiring high durability, rigidity, and impact resistance. These parts may be geometrically simple but thick and heavy, aligning with the goal of reducing part counts and enhancing vehicle durability. In contrast, the 50,000-ton Giga Press aims to cast the main body of the Tesla bot, a compact, lightweight yet extremely intricate structure that must integrate mechanical mounts, motor housings, wiring channels, sensors, and numerous high-precision assembly points. Casting a robot frame in a single press cycle, while still incorporating all internal mechanical structures, is a tremendous technical challenge, requiring far higher precision than vehicle frame casting. Next, the alloy materials used in casting show clear differences. For the Cybertruck, Tesla uses ultra-hard aluminum alloys cast into thick plates to ensure resistance to impact and heavy loads during operation. However, the Tesla bot requires a completely different alloy and aluminum-magnesium, lightweight but strong alloy that makes the robot frame both sturdy and keeps the overall robot weight optimized under 60 kilograms. This is crucial for enabling flexible movement, low energy consumption, and compatibility with the small electric motor systems inside. Additionally, the mold precision and allowable tolerances during casting are decisive factors. For the Tesla bot, allowable deviations in mounting holes, rotary shafts, and transmission brackets must be extremely small, sometimes only a few thousandths of a millimeter, to ensure smooth movement and accurate manipulation. Therefore, molds for the 50,000-ton Giga Press are manufactured using advanced technology, more expensive materials, and are designed for wear resistance and precision retention over millions of press cycles. In contrast, the 12,000-ton Giga Press molds can tolerate slightly larger deviations, given the larger product size and less stringent micro-level detail requirements compared to robots. Another important distinction is the production cycle time and casting speed. The 50,000-ton Giga Press can complete a Tesla bot frame in about 60 to 90 seconds, since it melts less alloy and deals with a smaller product structure. Meanwhile, the 12,000-ton machine takes 2 to 3 minutes per cycle to cast a Cybertruck frame due to the larger material volume and longer cooling times. Faster casting speed is critical for Tesla to reach high production volumes for Optimus, about 10,000 robots per week in the near future. Once again, please help us reach 8,000 subscribers. This is important for us to stay motivated. Thank you. Why is Giga Texas suitable for producing Tesla bot using the 50,000-ton Giga Press? Tesla Giga Texas is currently the leading candidate to implement the 50,000-ton Giga Press casting technology for the Optimus robot, based on many technical advantages and Tesla's overall production strategy. Giga Texas covers more than 9,200 hectares and is considered the largest automotive manufacturing facility in North America, with a projected capacity of up to 500,000 vehicles per year, including the Cybertruck and electric vehicle, pioneering the use of the 50,000-ton Giga Press technology to cast large structural components in the vehicle frame, significantly reducing assembly time and production costs. According to published data, the 50,000-ton Giga Press can cast large parts measuring several meters in size in under 2 minutes per cycle. This pressing force is approximately 4 times greater than the 12,000-ton Giga Press, currently used for other Tesla electric models such as the Model Y. Using the extremely high-pressure Giga Press allows for creating large, single-piece components that minimize joints and separate parts, thereby increasing durability and reducing weight factors that are crucial for the Optimus robot's design. Not only equipped with modern Giga Press production lines, Giga Texas also has a top-tier team of mechanical engineers, AI experts, and automation specialists with experience in developing complex systems such as robots, electric vehicles, and control software. The synchronization between casting technology, robot design, and advanced electronics enables Tesla to significantly shorten product development cycles and increase the feasibility of mass-producing humanoid robots. Furthermore, the factory has dedicated testing areas for Optimus, allowing quality and functionality checks immediately after assembly. If the production and casting process at Giga Texas proves successful, Tesla will likely expand this technology to Giga Berlin and Giga Shanghai. Giga Berlin, Tesla's main production hub in Europe, is designed for up to 500,000 vehicles per year and is equipped with advanced technology and highly skilled labor. Although labor costs are higher there than in China, producing close to the EU market helps Tesla reduce logistics and tariff expenses and quickly meet the rapidly growing demand for robots in Europe. Meanwhile, Giga Shanghai offers production costs approximately 40 to 60% lower than in the US, especially for labor and logistics. With a capacity exceeding 450,000 vehicles per year, this factory could become a large-scale production center for Optimus robots serving the vast Asian market, including China, Japan, South Korea, and Southeast Asia regions, with high demand for automation in industries, logistics, and services. Tesla's multi-factory production strategy combined with Giga Press technology increases flexibility in the global supply chain, minimizing risks of disruption due to political, economic, or logistical factors. This approach also shortens delivery times and improves Tesla's ability to meet the growing market demand for robots. However, deploying the 50,000-ton Giga Press for humanoid robot production across different factories poses significant challenges, including standardizing technical processes, workforce training, and maintaining product quality in diverse manufacturing environments. Tesla will need to invest heavily in training and build strict management systems based on its global experience ramping up electric vehicle production. Regarding long-term goals, we appreciate your contributions and hope you will have the most relaxing feelings after watching this video. If you did, please hit the like button and join the Techno creator family by subscribing to our channel. And don't miss out on any of our awesome videos by hitting the bell icon. We value your feedback and your time. Thank you so much for watching, and we'll see you soon. Until then, stay safe and have fun.